Welcome back to Multigrid Methods. We're in Chapter 9, and so my agenda for today is to do a review of what we've done in Chapter 9 so far, talking about the basic theory of additive subspace preconditioners, and in particular talking about the hierarchical basis preconditioner specifically. So again, we're in Chapter 9. There's two parts to this slide deck. We're going to go through Chapter 1, or sorry, Part 1. Again, that's something we've already done, but I'm going to go through it rather rapidly so that we can do something of a review of that. So the idea with with preconditioners is we want to solve an equation of the type A U equals F, but instead of solving it directly using let's say Gaussian elimination. And instead of using multigrid methods, what we want to do is to use an iterative method like the conjugate gradient or the steepest descent method. And one thing that we can do when we use either of those two methods is use what's called a preconditioning strategy. And that is we're going to pre-multiply both sides of this equation by a preconditioning matrix B. Now, this seems silly because we've done nothing. And if we want to solve this by a Gauss elimination method, we've just created a lot more work for ourselves because we've created a new stiffness matrix that we've got to invert. We've created a new right-hand side. This would require doing a multiplication and then perhaps running our Gauss elimination algorithm to invert that. But that's not exactly what we want to do. We're going to apply this sort of at a theoretical basis. And so when we apply this preconditioner B times A, we're looking for a B which is somehow very close to the structure of A, so that the condition number of this, which I'll explain momentarily, is very close to 1, or as close to 1 as we can get it. Now, let me preface this by saying that this theory that we're about to develop works quite well as long as the matrix A has some sort of known structure and it's symmetric positive definite, or Hermitian positive definite in the case of complex matrices. This strategy that we're going to talk about doesn't necessarily apply in general. It applies for symmetric positive definite matrix systems. So we're looking for a B, which is a good approximation of a inverse. And if it's, let's say it's exactly A inverse, then this would be the identity, and that's a perfectly conditioned matrix. Well, we won't get so lucky as to be able to find a B which makes this the identity, but we might be able to get close so that the difference between the minimum eigenvalue and the maximum eigenvalue is small, so that their ratio is close to 1 and therefore the condition number is close to 1. So that's what we're trying to do here. We're trying to apply some sort of strategy to find a preconditioner which makes this condition number small, which allows us to apply a conjugate gradient or a steepest descent type of method. Now, what does this have to do with multigrid methods? Well, it turns out that the strategy for doing this isn't exactly the same as multigrid, but it's very closely related to multigrid. And in fact, we can actually use multigrid as a preconditioner. It turns out one iteration of a V-cycle precondition or V-cycle multigrid algorithm is a pretty good preconditioner for a symmetric positive definite system that can be used in conjunction with conjugate gradient methods. So there is a very close relationship with what we're about to do with these subspace decompositions for building preconditioner matrices and the topic of multigrid that we've been discussing for the past 14, 15 weeks. So this is all in the way of a review. So I want to go through this rather quickly, and hopefully that you recall a lot of these details and topics. But please do stop me if you find any typos or any inconsistencies or any confusion Let's get that fixed up as soon as possible. So suppose that n is some positive integer, and we have a collection of integers, all positive, that have this hierarchical structure. M0 is less than or equal to M1, which is less than or equal to ML, which is less than or equal to N. And consider the following matrices Qj. Qj are tall and thin matrices. That's because they have the number of columns equal to n, which is this large number here, and the number of number of rows is equal to n, and the number of columns is equal to mj, which is maybe significantly less. So this could be like 20, and this could be equal to 5. So it's a tall and thin matrix. So such a matrix we're going to call a prolongation matrix as long as its rank is equal to the lesser of those two numbers, which in this case is mj. So each of these qj matrices has to be a full rank. If they're full rank, then we're going to call them a prolongation matrix. And now you might say, well, that doesn't make sense. You know, prolongation matrix from the point of view of multigrid has a very specific function and form, and that's true. But we're going to use that. It turns out, you know, when we're developing this in a very general way, this is good enough. This is a good enough definition for these things called prolongation matrices. We just need them to be, or to have full rank. So they should have full rank for each j from 0 up to L. So let this be a collection of those prolongation matrices. Notice that they're not all the same size. Okay, so one might be n by 3, and one might be n by 4, and one might be n by 5, okay, or n by 6. They're not all the same size. They're all different sizes, but we're going to group them together in a collection. We say that assumption SS1 holds for this collection, or we say that this collection supports a subspace decomposition of Rn. Notice Rn is kind of like our parent space, our space above all other spaces. If and only if, for each u in Rn, there exists vectors wj, each of which is in Rmj. So this would be like R4 or R5 or R6, like I said in the example, such that U is equal to the sum of the projection matrices, prolongation matrices, sorry, times these coordinate vectors, if you like. So in other words, we just need to be able to, these are kind of small vectors, and this is a large vector. And so what this is saying is these small vectors get expanded through the action of this Qj. Each one of them gets expanded. And basically what we're doing is, you can think about it as padding with zeros, those areas which it doesn't have information, so such that wj isn't quite as big as u. So, and I'll show you a very specific example of what I mean in a second. So we're kind of expanding these short vectors, and then we're going to add them all together. And if we can add them all together and always get u, then we say that assumption SS1 holds. Okay, so you're given the QJs, you're given a u, any u, and you've got to be able to find these WJs so that you can have this expansion. Well, we've already gone through these pretty simple examples, but I'd like to go through them again just so that we're all on the same page. For example, for these QJs, I can take them to be matrices having a bunch of rows and one column. So let's take them to have n rows and one column. So these are basically column vectors, right? So now, if you give me un, how can I use these matrices, multiplying them against some numbers, and then get back to u? So what I want to find is, can I find wj so that I can do the sum j equals 0 to L qj wj and get back to L? And the answer is yes. So here's an example of how I can do this. So QJs I'm just going to take to be equal to these matrices. Now these matrices are very specific ones. They're the column vectors which have ones in the j plus first entries. Now I have to use j plus first because the counting of this starts with 0. So the first one is going to be correspond to j equals 0, so that would be the first entry, has a 1 in it. So these are just the canonical basis vectors. Well, what I'm going to do is I'm just going to observe that U can be written as U1, U2 up to UN, and I'm going to take apart this vector in these pieces, U1, U2 up to UN. So I'm going to set, just formally, Wj vector equal to Uj plus 1. So the first one is going to be this one. Okay, so the first vector is actually a 1 by 1 vector, so it's actually just a scalar. Let's see if that makes sense. So if I multiply a scalar times this vector, does that make sense? Yeah, I mean, it's just going to give us a vector, and the result of that is just going to have the entry j in this position. And so when I add them all back, I'm just basically adding all the components of u back to each other. I'm throwing in a bunch of zeros otherwise for each one of these wj's. And when I add them back, I get u. So this is kind of the most trivial example of this, how these prolongation matrices could be constructed. This is too trivial though, and not useful for our purposes. Now, I asked you guys last time as we were going through this to have a look at this example. I believe you guys came up with some quite a nice analysis of this. So in this example, we're doing is essentially using the hierarchical basis, although I wasn't telling you necessarily where it was coming from before. But the idea is this. We're going to start out with n equals 7, so that's we're going to grab a u, which is generically in the space R7. And the question is, how can I build these matrices, these Q matrices, and then how can I find vectors so that I can rearrange things to add back to get u? Well, here's how I'm going to do this. I'm going to take Q2. It's kind of easier for me if I think about taking the Q2 first. So basically what I'm doing is taking all of the odd canonical basis vectors, E1, E3, E5 up to E7. So 7 is the value of n. All right, so that gives me a Q matrix, which is 7 by 4, because each one of these has 7 rows, and there are 4 columns, so 7 by 4. So I've used up all of the odd numbers going from 1 to 7. The next thing I'm going to do is start with 2, and I'm going to skip 4, and so that gives me E2 and E6. And if you know a little bit or remember a little bit about hierarchical basis, you'll see where this is coming from. We'll review this momentarily. So now I've used up E1, E2, E3, and E4 is missing. So E4 is the only one that's missing, and I'm going to supply that one for Q0. And I don't need to do any skipping for that. It's just going to be a matrix of size 7 by 1. So these are the 3 matrices that I'm going to use, Q0, Q1, Q2. Remember, U is generically in R7. So where's the information going to come from for this? Well, corresponding to Q2, I'm going to use W2. And W2 is going to have the following information in it: U1, Q3, U5, U7. So that's just the odd entries of U. Likewise, for W1, I start with 2 and I skip 4. So I go U2 to U6. And then the only one that I'm missing now is U4. So I'm going to grab that. So now you'll see, without too much trouble, I hope, that if I multiply Q2 times W2, I get all of the odd components for U. And if I multiply Q1 times this vector, U2 and U6, I get components U2 and U6 back, and zeros everywhere else. And the same with this one. I get the component for U4 and zeros everywhere else. And such that when I add these guys back together, I'm going to get U. They slot in exactly in the right positions. So the first one gives me something like U1, 0, U2, 0, U3, 0. Let's see, not U2. U3, U5, 0, U7. So that's the one coming from this vector. Okay, once I arrange it. And then this one is going to give me two components, just U2, 0, 0, and then U6. Got to put enough zeros in there. And then finally, this last one is just going to be U4 and zeros everywhere else. And so when I add those back up, I get U1 through U7. So this is what's called hierarchical basis. And the picture for this actually illustrates what's going on quite nicely. So once you visualize this hierarchical basis, it becomes much more sensible what's going on. And we'll do that momentarily. Here's another example of hierarchical basis. And this one I can't write out because there's too many components. So n is equal to 23 in this case. And so I'm going to take the following numbers. M0 is equal to 2, M1 is equal to 3, M2 is 6, M3 is 12. Basically, M3 represents the number of odd numbers going from 1 up to 23. Then these numbers here, I start with 2 and I skip by 4, etc. These numbers, by the way, when I sum them up, have to add up to n. Okay, as they do, they add up to 23. And here are the matrices that I need. So remember, this one is the collection of the odd indices, or these are the canonical basis vectors associated to the odd indices. Then I start with 2, skip by 4. Then I start with 4, because 4 was skipped, and I'm going to skip by 8. Then I go to 8, which is the one which is skipped next, and I only have to skip out to 16 to get the next one. So there's a pattern here that you follow. It might seem a little bit strange because I'm skipping 8 here and I'm also skipping 8 here, so that doesn't kind of make sense, but you have to change your strategy once you get to the 0 level. Now, for the W's that I want to use in this case, well, it's the same strategy. I just pick the indices of U for U3 associated to the all odd indices. For W2, I start with U2, skip 4. For W1, I start with with index 4 and I skip 8. And then I have to do something a little bit different for W0. I grab the last 2. So if I add all of these guys back up in this fashion, you'll see that I get U. Now, in this strategy of doing things, this hierarchical basis strategy, this decomposition is always going to be unique. There's no other way to do this decomposition using these matrices. And that's because they're kind of mutually disjoint from each other. They don't contain the same indices, so there's no overlap. So the only way to get the odd indices is to get them exactly right from here. The only way to get these indices correct is to get them exactly right, and so on and so forth. So there's really only one way to do this decomposition. It's unique. So that leads to the uniqueness property of the hierarchical basis. Before we get on to that or get into that any deeper, before I get on to talking about hierarchical basis, let me talk about generic additive subspace preconditioners based on these prolongation matrices. So the idea is you're given some collection of prolongation matrices, don't have to be based on a hierarchical basis, could be derived from anything as long as they satisfy property SS1. And now I want to use these to build a preconditioner. And I want to do this in such a way as to build what's called an additive preconditioner. Suppose that assumption SS1 holds for the prolongation matrices. The matrix C, which is a square matrix, is called an additive subspace preconditioner with respect to these prolongation matrices, if and only if there are SPD matrices CL, each of which are square. They have to be square to be SPD. And notice they vary in size. So starting with L equals 0, they get larger and larger and larger as I go to L equals capital L. I'm going to assemble them together using the Q matrices to form a big matrix. The way I'm going to do this is C is going to be the sum of a bunch of matrices, each of which turn out to be square, and size n by n. Now here inside, CL is a matrix, CL inverse is this matrix inverse, and it's therefore size ml by ml. I'm going to pre-multiply it by QL and post-multiply it by QL transpose, which I call ZL. QL transpose is ZL. Okay, so QL is n by ml, n by ml. This is ml by ml, and this is ml by n. So each one of these guys, once I make this product, is n by n, and therefore C has to be n by n. Okay, ZL is just the standard transpose, the canonical transpose of the QL matrix. Okay, you just transpose the rows and the columns as usual, which is exactly what's going on here. Let's make sure that everything makes sense in terms of multiplication. So QL, this is n by ml times an ml vector. So this becomes an n vector. And this is an n vector. If I don't write anything in the bottom here, this means the canonical inner product for Rn. Okay, and if I take the transpose of this, it goes to the other side, right? In the standard canonical inner product, an adjoint is a transpose. So the adjoint goes to the other side, it becomes the transpose. But now I have to ratchet my inner product from N to ML. So this is my ML inner product as usual. So before we put a subscript L, if it was the NL inner product, we're going to carry on that same tradition with the ML inner product. And so this guy here, this is ML by N. This is size N. And so this is now a ML vector. This is an ML vector. Okay, everything makes sense. Good. And so I'm just replacing this with its definition here because that ZL is defined as that. Okay. Now, just a remark to follow up with what I just said. My notation in this chapter is that if I don't put anything here, that's going to just represent the standard Euclidean product, inner product on Rn. And if I put a subscript, that's the standard Euclidean product on RML. So we've started using ML instead of NL in this chapter. Not sure exactly. Well, yeah, I am sure. I do know why, and you'll see why once we get to defining the hierarchical bases later on. But okay, so we have to be a little bit careful because if we have an L here, does that represent the inner product for ML or NL? You know, we have to be a little bit careful. If we have just a norm, that's just going to represent the standard Euclidean norm on Rn. And if we have a subscript L, that's the standard Euclidean norm on ML, RML. Okay, suppose that assumption SS1 holds for the set of prolongation matrices, and C is a preconditioner with respect to this family. Then C is SPD with respect to the canonical inner product. And consequently, if A is also SPD with respect to that, then the product is SPD with respect to these two inner products. So we're not going to reprove this. If you know, if you recall a few facts that we proved way back in chapter 1 and discuss again in this chapter, if we know that C is SPD, which we're not going to prove because it's a fairly straightforward proof to carry that out, then if I multiply the two matrices together, A or C times A, then the product is no longer symmetric with respect to the canonical inner product. However, it is SPD with respect to these two inner products, either one of those two that you choose. And therefore, if it's SPD with respect to some inner product, what we know is that its eigenvalues are all positive. It has a basis of eigenvectors That is, the space has a basis of eigenvectors for this product matrix. And basically, the spectral decomposition theorem holds with respect to that. Okay, so again, we're not going to prove that. This just follows, we proved this last semester, and it follows from the fact that we're assuming that this property SS1 holds. Okay, so um, you can go through that if you would like to refresh your memory on that. Suppose that assumption SS1 holds for the set of prolongation matrices QL, and suppose that U is fixed, then the set QU is what I call uh, a Q class of U. Q class of U. So what is the Q class of U? Well, if I fix these matrices, these prolongation matrices, and SS1 holds, and U is some fixed number, I know that I can always find a collection of WJs so that I can reconstruct U. Okay, so that's what SS1 means. I can always find some WJs so that I can reconstruct U. Basically, this is like a coordinate representation for this guy using these matrices, kind of. Well, now we said for the hierarchical basis, there's only one way to do this. So that means in the Q class, there's only one set of vectors which are going to work. There's a unique set. It's kind of like saying it has a unique representation. However, for other classes of prolongation matrices, these representative vectors, WJ, these coordinate vectors, are not necessarily unique. There might be a bunch of these in the collection. So these are therefore all of those collections of WJs which can rebuild U through this process. So in other words, they're all the different coordinate representations of U. They may not be unique, so there could be a lot of them. However, they could be, like in the case of the hierarchical basis, unique, and therefore there's only one there's only one in the class. Okay, so now just for shorthand, we're going to write, if we want to draw out an element from the class, we're just going to say this guy is from this class or this set. Now notice that this is a little bit weird because these coordinates are all different sizes. WJ vectors are like one is size 1 and one size 2, one size 3, etc. Just like in the case of the hierarchical basis, each one of these W vectors was of a different size. So when I put them together in a collection, it's not like a set in the usual sense, right? So I'm going to say that these are kind of an ordered tuple. The order matters. Okay, you can't reshuffle them or anything. Order is very important in this case. Okay, so remember, for some collections of prolongation matrices, this process may not be unique, and therefore I could get a lot of members in this class. If it is unique, then there's only one element in the class. And these classes they're not spaces. You can't add elements together to get another element in the spaces. They're just sets. Suppose that assumption SS1 holds for the set of prolongation matrices, and C is a preconditioner with respect to this family. Then, for any U in Rn, U measured in this inner product against itself, so this is the C inverse inner product, where C is that preconditioner. This can be represented in a very, I wouldn't call it a simple way, but a different way. It's the minimum over every representative from the Q class of U. Okay, so this is a tuple from the Q class of U over all of these sums, CL, WL, WL, L. So this means the inner product in ML, etc. Well, we know, well, first of all, what do we know about this? As long as this guy is non-zero, this has to be greater than 0, right? So each one of these guys should be a positive number each time I add them up. Okay, or I should say each one of these when I do it. And that is indeed the case because each one of these is symmetric positive definite. These are vectors. Now these vectors could themselves, one or two of them could be zeros, I guess. But not all of them can be zeros. Well, then once we get that collection, we're going to take the minimum over all the possible choices of W, L, and the Q class, right? So this is very strange, but it turns out to be quite useful and quite a nice tool for us for when we want to estimate the sizes of eigenvalues and well of the maximum and the minimum eigenvalues. And that's because I'm going to skip the proof because we did it last time. And that's because of this little result here, the eigenvalues of CA. Well, normally the eigenvalues of CA have this representation, okay? We can represent the max and the min through something called the Rayleigh quotient. So this is nothing more than the Rayleigh quotient type of law or the Rayleigh quotient formula for the maximum eigenvalue of the product CA. And now my last little lemma told me I could replace this guy with the min, okay? So all I have to do is when I calculate this guy, instead of using this thing on the bottom, I'm going to use this thing on the bottom. I'm going to replace it. Now, again, this doesn't look like I've done anything which is going to help me or serve me in any way, shape, or form. It doesn't look like it's made my life any easier, but it has actually. It's going to allow me to analyze the eigenvalues of this product matrix much more easily. So that was for the max. For the max, I take a maximum over the Rayleigh quotient. For the min, I take the min over the Rayleigh quotient, but I still do the same replacement, and therefore I get the same sort of formula. The only difference is max goes with max here, min goes with min here. And so this is just updated or a modified version of the Rayleigh quotient formula for the max and the min eigenvalue. And it turns out, as I said, that this gives us quite a nice calculation tool. Now, the proof again is a two-liner because if you believe the lemma, the last lemma whose proof we skipped, if you believe the Rayleigh quotient, then it's just a simple replacement. So the proof is actually rather trivial. It's just I want to remind you that when we use this again from time to time, its form is quite ugly and it doesn't look like it's helpful in any way, shape, or form, but it actually turns out to be. All right, so the next section in this chapter is hierarchical basis. Again, this is a review, so I'm going to go through this rather quickly. So what do we do in hierarchical basis? Well, one of the key components of hierarchical basis is this idea of this nested refinement, how we're taking a primordial mesh and we're refining it step by step through a process called bisection and quadrisection. So bisection is what we do in 1D to obtain a finer mesh. So for example, if I have an element which looks like that, or that might be the whole mesh actually, to refine this, I'm just going to put a point right in the dead center. So that's bisection. I'm going to bisect this line segment. And that gives me two congruent elements that are kind of similar to the shape of the first, right? Well, the shape of the first is just a line, so there's not much changing there. You can see, though, it makes a little bit more sense what I'm saying in 2D. You start off with an element, and we're going to refine this by quadrisection. And quadrisection means I take every edge, and I'm going to put its midpoint in, and then I connect the midpoints up, and that gives me four congruent, well, similar triangles. And so, not congruent, but similar triangles. So you can see that here. So this way of building up this mesh through bisection and quadrisection gives us a lot of nice properties. For example, it allows us to construct very quickly the basis elements, for example. It gives us a lot of geometric information about this problem very quickly. So sometimes multigrid is broken up into two sort of flavors, and one is what you would call algebraic multigrid and what's a geometric multigrid. I haven't really made the distinction between the two, and the reason is because we're using exclusively the geometric multigrid flavor. That is, whenever we encounter a mesh which looks something like this, we're always going to assume that the way we get a refinement is through quadrisection. So that tells us everything about the mesh once we know the coarses level mesh. Well, we're going to use this concept to build what's called a hierarchical basis. To do so, let me introduce my regular finite element families. Okay, so whether it's 2D or 1D, what we do is we start off with omega, which is in 2D, it's just going to be an open convex polygonal domain. By polygonal, that means I can put a triangulation on it. Okay, and I can divide it up into triangles, each of which is conforming. That means whenever I have two triangles coming together, I don't have anything like a hanging node. So we talked a little bit about that before. And so I can always put a nice conforming partition or a triangulation onto this open convex polygonal domain. The convex isn't necessary for the construction of the partitions or the triangulations, but it's useful technical assumption. All right, so I guess the best thing to do is to fix your gaze on either 1D or 2D, whichever you find to be easier to understand. I'm gonna think about 2D. Okay, so I'm gonna think about something, maybe a domain which looks like that. Okay, so I can put a triangulation on it, initial one, and then I can quadrisect that to make even finer triangulations, each of which turn out to be conforming. Okay, they always give me nice finite element spaces, and I can keep going with this, keep quadrisecting. So this family of triangulations is what we call TL. So the first triangulation I drew was T0, and then the next one was this one you're seeing here is T1. So T2 would be a quadrisection of that and the collection of all of those triangles. Okay, so now I'm going to build finite element spaces from that. So the two finite element spaces I'm going to build are SL and VL. So SL is going to be this collection of all V's, which are continuous, on this domain, such that when I restrict V to any triangle in the mesh, then I get a linear function. So when I restrict to a triangle, I get basically a plane. So this is what's called the piecewise linear finite element space. Notice that they have to be globally continuous. So that means there has to be some sort of continuity structure across going from one triangle to the next. All right. It has to be piecewise linear on each triangle and globally continuous. And I'm not going to supply any boundary conditions with this definition. However, the space VL is going to be defined with boundary conditions. It's just going to be a collection of all V's from SL that are 0 on the boundary. So their degrees of freedom are basically wiped out on the boundary. I set all their degrees of freedom just to be 0. So those degrees of freedom are eliminated. Okay, they're no longer degrees of freedom, they're fixed degrees. Now I'm going to define NL to be the dimension of VL, and I'm going to define some new spaces called W spaces. So W0 is equal to V0, okay? W0 is equal to V0, they're the same. But once I have L being bigger than or equal to 1, these WL spaces are going to be defined differently from VLs. So here's how they're defined. WL is equal to this collection of all V from VL such that if I look at all of the nodes in the relative coarse mesh, then those degrees of freedom are eliminated from V. In other words, I'm going to specifically set those that information that is V at each node from the coarse mesh. These are the nodes from the coarse mesh have to be equal to 0. I'm going to show you a picture of this momentarily because it's hard to picture otherwise. So this NLJ or NL minus 1J, these are what we call the sets of interior vertices of the triangles, okay? So for example, for T2, the interior vertices are here, here, here. So there are 1, 2, 3, 1, 2, 3, 4, 5, 6 of them. And if I refine things, I'm going to get more degrees of freedom, but it's going to look like a mess, okay? So This is the set of interior vertices. The number of those is always going to be NL. And that, by the way, gives us the dimension of the space, if you recall. WL is the set of all functions from that space where the degrees of freedom from the previous mesh have been set to 0. So let's go back to this example. The only degree of freedom that appeared in the previous mesh was this guy, okay? So that means that one of the degrees of freedom is eliminated on W2. Namely, this guy has to be set equal to 0. All the rest of them, these 5, can be non-zero. But the one for this degree of freedom, because it was associated with the coarse mesh, has to be set equal to 0. That's how we're prescribing these WLs. So that's how W2 would be defined. We're going to set ML to be equal to the dimension of WL, assuming that it is a space, and it turns out it is. All we're doing is we're taking a subspace of VL and we're setting some of the elements to be equal to 0. So if I zero out certain components of elements from VL, then that's going to give me a subspace. I can add functions together in that subspace and from that set, and I get back in the subspace. So it's clearly a subspace. It must have some dimension. The dimension must be less than NL, and we're going to call that dimension ML. And that's why I used ML previously. By BLV, we're going to denote the family of Lagrange nodal basis elements, basis functions for VL. So BLV is phi LJ, J equals 1 to NL. So that's the basis elements that we constructed in chapter 6. Those are the ones you're familiar with. And remember, the Lagrange nodal basis has this property that if I evaluate psi LJ at the interior vertex, NLI, I get delta IJ. Okay, so that's the Kronecker delta symbol. So this is the standard way of defining the Lagrange nodal bases and the Lagrange nodal basis elements. Now, what about the hierarchical functions? Well, here's a sample of a hierarchical function. In fact, this is like a W, this would be like W2, okay? So if I look at a function from W2, L equals 2, what I'm going to do is I'm going to take the degrees of freedom that were associated to the coarse grid. Okay, so it's these guys here, and I'm going to force that function to be 0 at those points, at those 3 points. All the other points, it can take on arbitrary values. I don't care. So this is a sample function v from WL. In this case, L equals 2. Let's see, am I right here? Is it L equals 2? Maybe it's L equals 3. No, it's L equals 2. And so just notice that the way this is defined, V is equal to 0 at all of the nodes in the coarse mesh. That's what that means, coarse mesh nodes. So the fine mesh nodes are all of these guys. But remember, we're refining through this standard refinement procedure of bisection in the case of 1D mesh. So the mesh at the coarse level would be given by these 3 points. If you want to count those edge points too, you can. And then we just do a refinement by bisection. But we're not going to allow V to have degrees of freedom at these 3 points because those were nodes in the coarse mesh. Okay, so from this, this weird space, what we attempted to do before the break was to show that VL was equal to the direct sum of VL minus 1 plus WL. This makes sense because this guy is zeroed out at all of the degrees of freedom for VL minus 1. And the way we get this space VL is to add those degrees of freedom in, right? So if I think about how I created this, if I go from one space to the next, maybe I'll draw it here. So if I have a mesh like this, suppose that's my coarse mesh, and I have some function, the function is going to have degrees of freedom here, here, and here. And so the way I build the refinement is I'm going to add degrees of freedom at these 4 points. Now I've got 7 degrees of freedom. All right, so now that means that the way I've created this new space, okay, is by keeping the old space and then adding in the new space, okay, or adding these WL space, which doesn't have degrees of freedom at these 3 points, okay? So this should be kind of a natural decomposition. I'm adding just the new points here. These do not have degrees of freedom at the old points or at the nodes of the coarse mesh. Well, this is recursive, notice. VL is equal to VL minus 1 direct sum WL. And so what I can show ultimately, since W0 is equal to V0 because of this recursive structure, VL is equal to W0 direct sum W1 direct sum WL. Okay, so this we proved last time before the break, and so I won't go into that. But this is a way of thinking about using these new additional functions to enrich the old space, okay, in a direct sum. This proof is actually quite useful. So I do recommend, if you are a little bit confused about what's going on, to review this proof. It has a lot of nice details in it. But because I'm trying to save time and do a quick review, I'm going to skip over it. Well, now, and I'm going to define something mathematically, which is entirely correct as far as I know. But a picture is worth 1,000 symbols in this case. So all this symbol vomit is easily replaced by a nice picture. But bear with me just a second. All right, so we argued that WL was a space. I actually didn't write that, but I hope that that's clear. Since we're taking a subset of functions from a space and we're zeroing certain ones of them out, we're creating a new subspace with a size or dimension that's much smaller than the than VL. But it is a subspace, and therefore we can ask the question, well, what's the basis of this? What's a basis? So here's the way we're going to define the basis for this. Remember we said we forced the dimension to be ML. We just by fiat said that that's what the dimension was. And we're going to define these elements in the following way. Phi Li in WL is defined such that phi Li at NLJW is equal to the Kronecker delta symbol Dij. But now notice these are the nodal points for the W set, okay? And those are, to find the nodal points for W at level L, what we're going to take is all the nodal points, the interior vertices for our mesh, and we're going to remove all the nodes, all the vertices from the coarse mesh. Okay, so you take all the nodes and you remove all the ones from the coarse mesh, and that gives you all the nodes in the W space. Okay, and so that's an easy way to define a basis. Probably should have a little, yeah, I do. Okay, so a little lemma says that this is a bona fide basis for that. So that's left as an exercise, and I hope that makes sense. So here's again this W2 space. Remember what we do is when we construct W2, we look at the space V2, but we're going to reject the degrees of freedom at these 3 points. Okay, so this dimension of this space for W2 is only 4, whereas the dimension for V2 is actually 7. But we're going to reject these. Essentially what we're doing is we're rejecting these 3 basis elements. Okay, we're throwing those away. We're only keeping these guys. Why are we doing that? Well, the reason is because this W2 space nicely reconstructs the V space. In fact, the proof of that is through this little exercise. Okay, so the proof of it is through proving this, which I'm not going to do because we've already done it. but I think a picture can show you how this is working. And in fact, the example that we did earlier should show you as well. That's exactly what's going on with the hierarchical basis. All right, so this is the nodal basis functions for W2. Let's see, do I have anything else? This um, is a bona fide basis. It has exactly the right number of elements in it, and it's um, it's a spanning set and linearly independent, etc. What you need for a basis. All right, suppose that WL is these hierarchical spaces within VL. They're defined as earlier. Then we're going to define the hierarchical basis. And in fact, this is a hierarchical basis for VL. It's going to be defined as the union from J equals 0 to L of the hierarchical bases for the W spaces. Okay, so just take all the union of that and put those together, put those basis elements together, and this gives me something I'm going to call the hierarchical basis. In fact, the lemma claims that this is a bona fide basis for VL. I should have given it the definition hierarchical basis because that's what it is. So I'm not going to do the proof. The proof is something we've done already. But I think that the picture actually does, uh, you know, does more justice to the proof than the actual words do. So, for example, here's the hierarchical basis compared to the standard Lagrange nodal basis um, for V1. So what I do is here's the basis element for V0. For the hierarchical basis, I don't use this basis for the next one. What I'm going to do is just going to keep this hierarchical basis or this basis element from the 0 space, and I'm just going to add in these two new ones for the 1 space. Whereas for the standard basis, you always, these hat functions always have the same shape. I guess the way you can look at it is as the following. For standard Lagrange nodal basis, you always reconstruct the basis, and the basis elements always kind of look like each other. They're always like soldiers. They're always like carbon copies of each other, right? This is the first 3 soldiers, right? Um, But for the hierarchical basis, you don't it's kind of a reuse and recycle sort of thing. It reuses the basis element from the 0 level and just adds in the 2 new degrees of freedom that you would have had to have in order to get the next level. And I hope that you can see that these basis elements are entirely able to capture in linear combinations any arbitrary function from V1, just as this guy is. Now it's a little bit more complicated to write down what are the coordinates in this basis. It's a little bit easier to imagine what the coordinates are from this basis, but this hierarchical basis does it differently. And that's about all you can say at the moment. It's going to do things differently, and it turns out the differently part about it is actually going to be useful. Now for V2, according to our standard construction, this would be our standard Euclidean basis for V2. Remember, all of the basis elements look like each other. Okay, they're all carbon copies of each other. There are 7 of them in V2. But for the hierarchical basis, again, it's a reuse and recycle sort of strategy. Here's the element from V0 and W0. From W2, or sorry, W1, we're going to introduce those 2 guys. Now we only have to introduce 4 new basis elements to get the W2 space. And now when we put all these guys together, this gives us 7 basis elements. And those 7 basis elements are just as good as these 7 basis elements. Okay. In some ways they're better. In some ways they're not quite as good. Now let's take a moment and say why finite element is kind of a useful strategy. Well, finite element works because the matrices in the finite element method, the stiffness matrices, are sparse matrices. And the reason they're sparse is because these basis elements are so narrow. Okay, so this kind of construction preserves the sparsity of the stiffness matrix for the finite element construction, whereas this guy does not. Okay, so this would not preserve the sparsity pattern that this preserves. Okay, however, this has some nice benefits, as we're going to see, especially when it comes to building these hierarchical basis preconditioners. So I think that's my last slide there. Yeah, it is. And so I'm going to go on to second slide deck and talk more about hierarchical basis. So now we know what a hierarchical basis is. Of course, again, this is all in way of review. So now we come to this very long section, and this one is like a really, really difficult section. And so I promise I'm not going to dwell a lot in it. I'm going to hit the highlights of it. I don't think we'll be able to finish it in the last 15 minutes that we have available to us today. But you know, however far we get, I'm not going to go into all the details that we did last time. We're just going to keep a high level review here. So now we want to construct a preconditioner based on hierarchical basis. So the one thing we know about hierarchical basis is we can get these Q matrices from them. And the reason why we know we can do this is because I showed you in the examples how to do this at least in one dimension. In two dimensions, it's a little bit more complicated, but it still works. So we want to build these um, prolongation matrices that are based on the hierarchical basis sort of structure. So how do we do this? Well, I could argue all day about how this is done geometrically, but let me go instead and do the algebraic definition. The one thing I do want to caution you on is something that I cautioned you on last time, is that the indices in this section can get a little bit overwhelming. So please pay attention and let me know if the indices in any way, shape, or form don't make any sense. All right, so we created these bases for the V and W spaces. Okay, so let BJW be phi j I equals 1 to MJ, BLV phi LI I equals 1 to NL be the usual bases. So this one is the Lagrange nodal basis for V. This is kind of the Lagrange nodal basis for W, not quite yet the hierarchical basis. You know, the hierarchical basis is when you take unions of these guys. All right, but in any case, they're bases for the space WJ and VL respectively. So now WJ is a vector subspace of VL because of the containment that we have and the fact that we have this sort of nested um, finite element grid structure. WJ is always a vector subspace of VL. Therefore, since these guys are elements of WJ, they must also be elements of V. Okay, so these basis elements. So that means that there are unique numbers that have four indices, sadly. Q, J, K, I, L. Okay, K goes from 1 to NL, I goes from 1 to MJ, such that phi JI, the basis elements for this, for the W space, phi JI is equal to the sum K equals 1 to NL, QJKIL, psi LK. So what this means is I can take any one of these guys and I can write it in a basis expansion for these basis elements because VJ happens to be a subspace, a vector subspace of VL. Sorry, I think I might have said that wrong. WJ is a vector subspace of VL. And some people write it like this. Vector subspace. Okay? That's the reason why I can do this. I can always find a basis expansion. So these are just the coordinates in that basis expansion, period. And so I can arrange these indices any way I want. Okay, the indices aren't so important. I just have to know here I'm summing from K equals 1 to NL because there are NL basis elements. Here, I have to know that there has to be, for this relationship to hold, I has to be between 1 and MJ because it has to hold for each one of these basis elements. Okay, so the proof of this is really nothing. I would just argue, okay, if you know this, then this has to be true. This is because there's basis representation, one line proof, done. So now I'm going to take those elements that I found in that previous little result, and I'm going to use those to define the entries of a matrix that I'm going to call QJL. QJL. So these are going to be my hierarchical prolongation matrices. So just take those elements that you get and the basis representation coordinates for the phi's in the space um, that has that basis, and I can create a matrix. Okay, so the only thing I have to make sure of is I get the dimensions right. So K is 1 to NL. So this number NL is bigger than MJ because they have to be tall, thin matrices. Okay, so that is the row index and that is the column index. So I think I'm good there. Okay, so this is a tall and thin matrix called the hierarchical prolongation matrix. All right. Now, a little lemma. Suppose that QJL is the hierarchical prolongation matrix and WJ is the coordinate vector of the function WJ with respect to the basis BJ. Okay, so this can be written, or sorry, this guy can be written in this basis, and when you do that, you get coordinates, right? So then the coordinate vector of WJ. Now WJ, because remember, I just said it and I'll say it again. So we have WJ is in capital WJ, and that's a vector subspace of VL. So that means I can skip this basis and write this guy in this basis. And here's how you do that. Well, once you know the Q matrices, you're done. And well, you need two things. I need to know the representation of this finite element function with respect to this basis BJW. And if I know that, then all I do is I take the Q matrix and I multiply that times that coordinate representation. And lo and behold, that gives me the coordinate representation of this function, but in this space with respect to that basis. Okay? And again, the proof is pretty straightforward, not too much trouble. All right, now another thing that I should point out about these spaces is they're not nested. The hierarchical spaces, WJ, are hierarchical but not nested. So W0 is not contained inside of W1 because this guy is kind of whatever is new from that space. So it doesn't contain the old, okay? So they're not nested. And furthermore, in chapter 8, we learned how to do multiplicative stacking of prolongation matrices. Well, you can't stack these prolongation matrices from the hierarchical basis. They don't stack. All right, so just a couple of things that are non-standard. But you can see all the things that are kind of related to the multigrid setting. We're using the mesh. We're using the fact that the mesh has some sort of really nice structure. We're using prolongation. We're just realizing that certain things don't quite work. Now, I want to tell you how you construct the hierarchical basis preconditioner um, and you know what that's all about. So the way I'm going to do this is I have to define the C matrices. So let's get into that. So I think last semester before the break, I did this a different way, and then I switched to some way which I think is a lot simpler, and I'm going to stick with the simpler way. So the way that's simpler is to define a bunch of bilinear forms for these CJs and then define matrices from the bilinear forms. Oh, but of course, actually, I don't even have to do that. It's just there's a technical reason why this bilinear form will become useful later on. So let's define a bilinear form CJ, which takes WJ, an element from WJ and another element from WJ and maps that to real numbers. That's what a bilinear form does. Now we don't know yet if this is an inner product, but for right now it's fairly easy to tell that it is bilinear. So the way we're going to construct this bilinear form is you take a function from wj and take another function from wj. Let's say wj and vj from this capital WJ. And what we're going to do is we're going to sum up the numbers r equals 1 to mj. So these are just the degrees of freedom from this space. And so we're going to evaluate wj at its nodes. So these are kind of what I would call the live nodes in the W space. Remember, the W space nodes are created by taking the V space nodes and then throwing away all the V space nodes that appeared in the coarse mesh. So roughly speaking, they have half the number of nodes. So these are the W space nodes, and you're going to evaluate WJ at those W space nodes, and the same with VJ. So these two things here are just numbers. Okay, they're just numbers. So when I evaluate them at those numbers, multiply them together and sum, I'm just getting a number, a real number. So this creates a bilinear form for us. All right, so let BJW be our standard usual basis for WJ. Then the matrix CJ, we're going to define the following way. So the matrix CJ is going to be a square RMJ by MJ matrix, and it's going to be defined the way you would define a stiffness matrix usually. You take your bilinear form and you're going to evaluate in the first and second components. You just evaluate the two different basis elements. And it's symmetric. It's fairly clear that it's symmetric, so I can interchange these two if I wanted to. So I'm just going to throw in the basis elements there. Now, what happens when I evaluate the basis elements at the nodes? Well, the basis elements are either 1 or 0 at the nodes, according to whether or not these two numbers I and R are equal. If they're equal, then it's a 1, and if they're not equal, it's a 0. Same here. If K and R are equal, then it's a 1, and if they're not equal, it's a 0. So that gives me two Kronecker delta symbols. And if I sum two Kronecker delta symbols in this way, I get just one Kronecker delta symbol. It's pretty easy to see that. And so what is this matrix then? Well, this matrix CJ with index I and K for its column and row index is just going to be a 1 or 0. Of course, that's just going to be the identity matrix because it's 1 whenever I is equal to K and 0 otherwise. So that's exactly what this matrix is. It's the identity matrix. Okay, so that's how we get started. It doesn't look like it's all that useful to us. We just define the identity matrix in some sort of weird, seemingly useless bilinear form, but it's actually going to be quite useful for us. So here's the hierarchical basis preconditioner, and I think we'll have to stop once I define this one today and pick up back with our review at this spot. Suppose that BLV is the usual basis for the finite element space VL. Suppose that AL is the SPD matrix defined via the usual way. Right, you take the bilinear form, the energy form for the system, and you're going to throw in the basis elements, and that's how you construct the stiffness matrix. It's SPD as we've seen before. Of course, this bilinear form is just equal to that usual thing for the energy inner product. The hierarchical basis preconditioner for AL is defined as CH. So this means C sub hierarchical. And I think I need to change that to a different font. Maybe a typo there. Okay. But in any case, the way I define it is I'm going to, I've already defined my matrices C, and so I need the inverses of those. But each one of those is equal to the identity, so there's nothing really here. I've already defined my Q matrices, the prolongation matrices, and ZL is just equal to the transpose of those. And so my preconditioner is just equal to the sum, L equals 0 to capital L, QL, capital L, ZL, capital L. So these are my prolongation matrices from the hierarchical basis, and these are their transposes. Okay, so notice that the title of this chapter is Additive Preconditioners. So why is it called an additive preconditioner? The reason it's called additive is because of this sum right here. Okay, the fact that I can sum these guys up. That's the additive part. Why is it called a preconditioner? Well, I'm going to multiply this times the stiffness matrix AL, and I'm going to show that when I do this, I get a condition number which is a lot closer to 1, or not very large, which is another way of saying that the ratio of the maximum eigenvalue to the minimum eigenvalue is very nearly 1. So that's what I aim to show in the next few slides. And again, the rest of this, lots and lots of details. I don't want to kill us with the details. I'm going to go through all that in one class, and then we're going to finish off the BPX preconditioner in one class. That's a different type of preconditioner, which uses the same theory. And again, both of these are related to multigrid methods. Not exactly multigrid methods, because we showed in chapter 8 that multigrid methods are what are called multiplicative methods, and these are additive methods, so these are somehow different. I'll stop there, and I'll take any questions that you guys have.